All right, let's see if you can hear me on this one. All right, so welcome everybody. This is our first Journey to the Sun talk of the year. And I want to ask how many people came to the Journey of the Eclipse talks last semester? So about a little over half of you. Great. So I'm glad to see everyone back. And this talk we're starting out, Dr. Corinne Brevik, who many of you have already met, I think, but she's been with us a few years in the School of Physics and Applied Physics as an associate professor. And she came to us from University of Colorado, where she got her PhD in astrophysics and planetary science. And she's on several of the research projects, one of them being SolarSTEAM that you see the banner for here. So she's going to talk to you about NASA's fleet of solar spacecraft today. So I'll let you take it.
Thank you so much. I need one tool for each hand. All right, so goal today is to give you sort of an overview of all the different spacecraft that NASA has that are designed to study the sun. So we can do that in one slide. Okay, I'm done. NASA put this graphic together. This is from their heliophysics division, and there's a lot of them. There's a lot of them. So we're not going to talk about all of them. I don't think you want to be here for the rest of the day. What we're going to do is talk about why they're there, the kinds of instruments they use, and then we'll highlight some of the ones that I think are extra cool. So we've got some old ones, some up-and-coming ones, some currently active ones. But you'll notice they're all the way up against the sun. Some of them are very far away. We even have a lander on Mars that's part of this project. The sun is big. There's so much we don't know that we just kind of keep picking away at it with one spacecraft at a time. All right, so before we talk about the spacecraft, let's talk about what they're doing. These spacecraft are each trying to pick away at a really, really large problem, and not one of them is going to answer all the questions. It's just not doable. So we're interested in, number one, how the sun works. We can't see the interior of the sun, so we want to know what's happening in the core, but we can't see it. And we want to know what's happening in the layers above the core, where you have photons of light slowly trying to escape the sun. And when they get a certain ways out, we start seeing convection. All of that's happening below the surface. What we can see are the surface layers. So the photosphere, that's the layer we take photos of. That's the layer that's giving off visible light. When we look at it, don't look at the sun, that's what you see. That's the photosphere. We can see the atmospheric layers above that. So as we go through these, you'll see them talking about the chromosphere and the corona. Those are the two layers of the atmosphere. The chromosphere is the lower layer. It's about 10,000 degrees. It primarily emits ultraviolet light. The corona is up to 1,000,000 degrees or more. It emits all wavelengths, but it emits a lot of X-rays. So one of the things we do is we look at the sun in different wavelengths. So if you look at 450 nanometers, which is in the visible, we can look at the surface, the photosphere. If we look in ultraviolet light, we get pictures of the chromosphere. If we look in X-rays, we get pictures of the corona. So we can see it like an onion by looking at different wavelengths. So these spacecraft look at all sorts of different wavelengths of light. We're also interested in all of the activity on the sun that comes from the crazy magnetic field of the sun. So sunspots, this is yesterday. The sun is currently approaching solar maximum. There are sunspots all over the place. So lots of sunspots. We're interested in how they form, why they form, when they form, how long they stick around. We're also interested in the attached phenomenon. So this is a solar prominence. There's a sunspot at each foot of this prominence. So that's part of the story. What's happening? Why is it happening? We're also interested in the ejections that come off of the sun. So we talk about flares. And because there's so many sunspots and the sun's so active, the sun is shooting off some crazy good flares right now. There's all sorts of stuff happening. So we're interested in flares, and then we're interested in these coronal mass ejections, which are these huge ejections that come out of the corona, like that one, and spew material into space. Harder to study from Earth, really nice if we can get out in space and really watch it occurring. Okay. And then we're interested in the sun's magnetic field and how that magnetic field interacts with the Earth's magnetic field. And we talk about the solar wind, which are particles constantly streaming off the sun. Kind of a low-level background of particles emanating from the sun. Those interact with our Earth. They hit our magnetic field. That affects us. So knowing what's happening, why it's happening, helps us predict what the effects on us will ultimately be. So we're interested in all these different things. In order to study them, we have a variety of instruments. And there's a lot of them, but there's kind of 4 fundamental instruments. So one of them is a camera, right? Take a picture. We get lots of information by taking pictures of the sun. We also use spectrometers. So this is a spectrometer off of the ACE spacecraft that we'll look at in a bit. Spectrometers take the incoming light and they break it up by wavelength. So it allows you to look at the behavior of individual wavelengths of light. So you'll see a lot of those. We also have particle detectors. So particle detectors can do things like simply count particles. This is the student dust counter off of the spacecraft that went to Pluto. It was literally counting dust particles. How many do we run across? They can also measure the energy of the particles. Some of them can measure the speed of the particles. Sometimes they can measure the kind of particle. So we're interested in what's out there. We tell little kids that space is a vacuum. Astronomers actually realize that what's out there is a whole lot of dust, and we love dust because that's what's in the vacuum of space. It's dust. And so we can study the dust and learn all about things. And then there's magnetometers. So magnetometers measure electric fields and magnetic fields. You can always tell when a spacecraft has a magnetometer on it because it's always on the end of a really long boom. So if you see a spacecraft and there's this big stick hanging out, there's a magnetometer on the end. What they're trying to do is get away from the interference of the spacecraft. You don't want to pick up the spacecraft itself. You want to pick up the magnetic field of the region it's in. So they stick it on a big pole. Okay. So as we look at these various spacecraft, you're going to see names of all these devices. But they're going to break down into one of those 4 categories typically. Okay, so with that in mind, let's go back to what's out there. Okay, again, we're not going to look at all of them, but we're going to start with this guy right here, who's the closest one. So this is the Parker Solar Probe. Parker is actively orbiting the sun right now. So it was launched in 2018, and Parker's goal is to understand why the corona is so hot. So on Earth, the atmosphere cools off as you go up, at least initially, as you gain altitude. On the sun, it doesn't work that way. The surface is 6,000. The corona is 1,000,000. As you go up in altitude, the temperature is increasing. We have a basic understanding of why that works, but the fundamental details we're still working on. So Parker's really interested in that. It's also really interested in these particles that come off the sun. It appears that a lot of them speed up after they get ejected, which also is weird because usually once you launch something, it slows down, but they're accelerating. So we want to know why. Couple interesting facts. Parker has a sun shield here, and I'll show you another picture in a minute. But Parker is so close to the sun, without that sun shield, you just fry all the electronics. So they put this 4.5-inch thick carbon shield there, and then it can withstand up to 2,500 degrees Fahrenheit. We protect the instruments. If Parker ever accidentally turned around and pointed the other direction, it would be toast. Quite literally, it would be done. It just can't point at the sun. So Parker was launched from the Earth, but in order to get it really close to the sun, it turns out they actually had to slow it down. So that's okay. People who do spacecraft usually like to do flybys of planets to gain energy, so you can speed up, but you can do it to slow down too. So they've been doing flybys of Venus, and every time it goes by Venus, it slows down a little, which allows it to get closer and closer and closer to the sun. So it's done 7 flybys, and the orbit gets a little bit less and closer to the sun every time. really big deal, Christmas Eve this year, Parker will get as close to the sun as it's going to get with the time window it's got to operate in. So Christmas Eve will be the closest approach. It will actually go inside the corona. It's the first spacecraft to ever get that close, which is pretty impressive because it's going to be flying through the atmosphere of the sun. So, fun fact, at the speed it's going, you could go from Philadelphia to DC in 1 second. Okay, that's with it slowed down. Okay, it's really booking out there. Now, Parker will reach the end of its original mission life shortly after that. NASA does this all the time. You have a standard mission. If you reach the end of your mission and your spacecraft is working, big gold star, everybody's happy. But then you don't kill the spacecraft if it's still working. They extend your mission and they give you more money, hopefully, and it goes longer. So there's a really good chance, Parker's working great, after this, if it gets an extended mission, it will continue to get even closer. So this probably will not be the closest Parker solar probe ever gets. Assuming it survives this closest approach, which it should, they'll continue to slow it down and get it closer and closer. Okay. So here's Parker from another angle. Here's that sun shield. Parker does have solar panels. When it's near the sun, let me back up. They look like this. They tuck them behind the sun shield. And then you'll notice its orbit takes it way out by the Earth. So when it's near the Earth, the solar panels come out and it can recharge the battery. And then, so they flap like wings. Parker has 4 instruments on it. The field instrument measures electric and magnetic fields. So there's our long stick pointing out the back. And then it has a particle detector that's measuring the kinds and the energies of the particles. It has an imager that's taking pictures of the atmosphere and the area around it. And it has a second particle detector. Really common if you're trying to study different kinds of particles, you need 2 different kinds of detectors because they're each set up for specific speeds and specific energies. So here one measures solar wind particles, the other one's measuring particles that are more high energy from the sun. And then on all of these, I've given you the website just for fun. Parker Solar Probe, though, is a really good one to visit. If you haven't been to their website, they have a chat feature called ParkerBot. If you click on ParkerBot, you can ask him questions about the sun and about the probe, and he's very smart. He will answer all your questions. Okay. All right, that's Parker. So the next one is ACE. ACE's job is to look at solar wind particles. So ACE is not taking a lot of pictures. ACE is interested in the particles coming from the sun, as well as these things we call galactic cosmic rays. They are particles that have come from outer space, from far away, usually outside the galaxy. They're very high energy. ACE is also interested in giving us warnings that there's been eruptions that are coming towards the Earth. So when we talk about space weather and geomagnetic storms, we're talking about these eruptions and what happens when they hit the Earth. And so it watches those particles and tells us what's happening. ACE is at an interesting spot. So ACE is at, whoops, wrong pointer. There we go. ACE is at the Lagrangian point. So ACE is not orbiting the Earth. ACE is not orbiting the sun. In between the Earth and the sun, if you think about the sun's pulling on the Earth is pulling on the sun, somewhere in the middle, there's a spot where the 2 gravities balance. That's the Lagrange point. It's the point where the sun's gravity balances the Earth's gravity. Sun is bigger. It has a stronger gravitational pull, so it can't be right in the middle. It's going to be closer to the Earth. But there's a balance point there where if you could plant yourself in your spacesuit, you shouldn't get pulled towards the sun and you shouldn't get pulled towards the Earth. We put spacecraft at that spot all the time. We don't, though, set them at that spot. We have them orbit around that. So it's like they're orbiting a planet, but they're orbiting a magic spot called the Lagrange point. The advantage of doing that is that you always stay between the Earth and the sun. So ACE always sees the sun from the same side that we see the sun. So it can stare at the sun and watch these particles coming. For our purposes, just to get a feel for where that is, If you start at the Earth and put 30 Earths side by side, you'd get out to where the moon is. The Lagrange point is 100 Earths away. So it's a little more than 3 times farther than the moon is. It's not out to Venus, that's too far, but it's between where our moon would be and where Venus is. Okay. So ACE was launched in 1997. It had a 5-year mission. It reached the end of the 5-year mission. It was going strong, so we just keep extending its life. We just keep getting data from it. Okay. So ACE has a whole plethora of experiments on it. You'll notice you don't see a lot of cameras. What you see on ACE, because it's interested in the particles, you see lots of spectrometers, and you see a few particle analyzers. So the spectrometers are each measuring different things. So it has a spectrometer that's going to measure the solar wind, and it has a spectrometer that's measuring the atoms, the isotopes from the sun, and it has a spectrometer that's measuring the cosmic rays coming from outside our galaxy. So lots and lots of spectrometers, lots of particle counters. It's really focused on particle data. But it's informing us about things like the northern lights. The northern lights occur when those particles enter our atmosphere. And it's informing us about like when these eruptions happen. If we get a flare, if we get a coronal mass ejection, what kind of particles get thrown at us? We know they're there, what are they? Okay, this one's actually my favorite. I don't really know why, except it makes pretty pictures and I like it. So this is SOHO. SOHO is a joint project between the European Space Agency, that's what ESA stands for, and NASA. So the European countries built a lot of the instruments that are on this, and then we launched it. It is run by NASA. We still do the mission control for it, but we share all the data. It is also orbiting at that Lagrange point. So it's between us and the sun. It always stares at the sun from the side the Earth is seeing. This one is full of cameras. It takes tons and tons of pictures. So whereas ACE was looking at particles, this one's going to be taking images. They're interested in how does this solar interior behave, which remember we can't see. So we're using the images of the outside to try to backtrack what's happening inside the sun. You're going to see some of these questions come up over and over. We want to know why the corona's hot. We keep learning more and more, but we're not all the way there yet. And we want to know why the solar wind is accelerated. Okay. So SOHO's been up for a while. They were one of the first to be staring at the sun with all these cameras, and I'll show you some pictures in a minute. But they got a lot of really important we were there first type discoveries. So they were the first to get pictures of the star's convective zone. So our sun convects. The hot material rises and the cold material sinks. And you can see evidence of that on the surface, right? You can't actually see the convective zone, but you can see kind of the top edge of it. They had extremely detailed measurements of the rotations that are occurring in the interior based on what we see on the outside, right? They got really good measurements of the solar wind, both the slow and fast particles. And this was really the beginning of this idea of watching for space weather. So when an eruption happens, we have a 3-day notification that stuff is coming. If you are a watcher of Northern Lights, right, you can sign up for websites that give you alerts, and they'll say, hey, there was an eruption on the sun. 2 days from now, go check for Northern Lights. No guarantees, but go check. So if you own satellites and you're like AT&T and your satellites are orbiting the Earth, you might want to shut your satellite off because there's a great big batch of charged particles coming this way, and we can save AT&T a fortune by not killing their satellites because they had warning. Okay. All right, so here's why I like SOHO. Really, really great pictures. This is the sun yesterday. So here's that picture we looked at earlier. You can see the sunspots. This is a magnetic field camera. So wherever the sunspots are, you're seeing north and south magnetic fields, and you'll notice they line up really well with the sunspots. And then there's a whole bunch of cameras that measure different wavelengths of light coming from the sun. So this is giving you a corona image. It's false colored, it's not really blue, but it helps us keep track of which wavelength's which. And you're seeing the atmosphere of the sun, so we can see arcs of plasma. There's sunspots, or the ones that are way over here on the corner. Okay, you can go into the SOHO website, and any day you can click on it, and it will show you the sun now. They also have combined these. You get really cool movies from the SOHO website. So you can watch the evolution of the magnetic field around the sunspots. You can see the filaments. You can see the plasma moving between the sunspots. And then it has a camera on it that is looking at the corona. But just like in white light, so this is visible light, but just like we don't see it normally, we have to wait for an eclipse to happen to see the corona, SOHO makes its own eclipse. There's actually a disk here inside the camera that they put over the sun. So we're blocking the sun so that we can see the fainter stuff around it. The sun is hiding behind that little circle. So we're ways away from the sun. What you're seeing here are the eruptions coming off the sun. Those are coronal mass ejections. So this is from 1998. You can watch time move forward quickly. But you can see these big ejections blowing off the sun. And sometimes those ejections come straight at us. And that's what happens when they hit the satellite. That's a huge amount of high energy particles hitting the satellite. It's really bad for the detector. And really, really bad if your spacecraft is not set up to handle it. That's the kind of things that the space weather people are watching for. Okay, and one more. If you're going to stare at the sun, you also see comets. SOHO has discovered literally over 3,000 comets, which wasn't one of their missions. But if you're going to stare at the sun and a comet comes by, you see it anyway. So we have lots of comets. This is Comet Neat. It came by in 2003. That's why I like it. It's very neat. Okay, so the next one is the Solar Dynamic Observatory. This is the next generation after SOHO. So SOHO was launched in 97. This was launched in 2010. It has a lot of the same features, but with much newer and better technology, right? Our imaging capabilities are just monumentally better than they were in 97. So we're still interested in space weather, solar activity, but with newer equipment and from a different orbit. The SDO satellite isn't at the Lagrangian, it's actually orbiting the Earth. But it orbits in a geosynchronous orbit, which is about 6 Earth radii out and highly inclined, so it's not usually blocked by the Earth. It goes way up and it goes way down. So we can always see the sun even though we're orbiting the Earth. It's really far away, and it's got a super tipped orbit. Okay. So it only has 3 instruments on it. So we can do the same types of things that SOHO was doing, but we only need 3 cameras because we're getting wiser and smarter, and our technology is just getting that much crisper. The cool thing is with these 3 cameras, we get better pictures. So this is SOHO. This is the exact same picture with SDO. You have 4 times better resolution with the new cameras. And we're getting way more data, which isn't actually always a good thing. But SOHO took 1 picture every 12 minutes. SDO is taking a picture every second. That's a lot of data that we're piling up to be analyzed. But we get similar images that are just so much higher quality. So these are the pictures out of SDO. You really can see the arcs of plasma coming out of the sunspots. And this is a really lovely prominence where you can see the shape of it. Okay, the Earth is not really there. It's just there for size perspective. All right, this is the next generation of the next generation. So SOHO was the beginning. SDO's active, both SOHO and SDO are still working. They're both actively taking images. MUSE is next. MUSE is going to do a similar thing. Its job is to stare at the sun, but with even better cameras. MUSE is a multi-slit camera. So the previous ones had single slits. By putting in 3 slits, turns out you can actually spread out the light better. You have more control over the wavelengths you're looking at. and the images are going to be even better. It hasn't launched yet. It's not even close to launch. Launch date is sometime in 2027, we hope, right? That's always truth with spacecraft. That's the plan. We'll see what happens. It is under construction. We're close enough, but you never know when delays are going to come in. However, give us a couple years and we can come back with even better pictures. This one will orbit where SOHO is at the Lagrange point. All right. Another one that is launching soon, this is PUNCH, which is a heck of an acronym. So PUNCH is going to be using polarized data. So light has a wave. Turns out light, that wave can go in different directions. Most of the time we don't care, but if you pay attention to the direction the light is oscillating, you get extra information. And so that's PUNCH is interested not only in where the light came from, but which way the wave is going. That will tell us what's happening. It's scheduled to launch in April, so they're really close, right? They're probably already at Kennedy getting ready to put things on the rockets. If not, soon. They're very close. So PUNCH will go into a polar low Earth orbit. So it's going to go over the North Pole, over the South Pole of the Earth, always pointing at the sun. So it will be on the dusk-dawn line. So it's just going to circle the Earth and stare at the sun. PUNCH is a particle detector. It's not interested in getting lots of pictures. It's interested in understanding the particles coming from the solar wind, the structures like those coronal mass ejections. The really cool thing about PUNCH is it's small. So these spacecraft we've been looking at are like SUV size to school bus size. They're big. PUNCH is about 1 meter. There's 4 of them. It's actually 4, they call them suitcase size, but that's a big suitcase. But 4 suitcase-sized spacecraft that work in a constellation together. So it's a smaller spacecraft that we have 4 of. Whoops, did I shut you off? Hold on. There it goes. So this is one PUNCH satellite, and every 8 minutes it rotates 30 degrees. So as it orbits, it keeps rotating. The point of rotating is to keep the Earth constantly below the spacecraft. Every time it rotates, it takes 7 images. It takes 1 unpolarized image. It takes 6 polarized images along with the particles it's looking at. So it rotates, collects data, rotates, collects data. Okay, and that whole constellation goes around. Yeah, the triangles and the squares just tell you like which satellite's which, because there's 4 of them. Okay. All right, one more. This is the beginning, right? It's great to talk about what's coming, but let's talk about where we started. So in 1977, NASA launched Voyagers 1 and 2. Voyager 1 and 2, a lot of people think about them related to planets, but Voyager 1 and 2 were collecting data in between the planets as well. So they were our first particle detectors, magnetic field detectors, electric field detectors, all the way out. So they were interested in all of interstellar space. They were interested in the magnetic field of the sun and how that magnetic field interacts with the planet's magnetic fields. Fun fact, they each have a golden record on them. This is, I don't remember if that's the one from 1 or 2, but they each have a golden record on them. The idea being, 5,000 years in the future when some random space life stumbles on our wandering spacecraft, there's information about humanity on the record, because these are leaving our solar system. So Voyager 1 went past Jupiter, it flew past Saturn, and then it did a gravitational slingshot around Saturn, and it left the solar system headed up out of the plane of the solar system. Voyager 2 also flew past Jupiter and Saturn, but then it kept going. So it flew past Uranus, it flew past Neptune, and then it did a gravitational assist down out of the plane of the solar system. So they are currently headed out in opposite directions. FYI, if you ever see really good pictures of Uranus and Neptune, they're still the Voyager pictures. Jupiter and Saturn, we've sent other spacecraft to. There's all sorts of cool images from Juno and Galileo and Cassini. Uranus and Neptune have never had another spacecraft visit them. So all of the images, they're okay. They're the best we've got, but it's 1970s images. Okay, taken in the 80s, but launched in the 70s. Notice it's got a magnetometer on it, right? There's that big boom sticking out again. So where are they now? Because they didn't stop, they're still going. So here's the plane of the solar system. Here's Voyager 1 that's headed up and out. Here's Voyager 2 that's headed down and out. As of today, Voyager 1 is 15.3 billion miles from the Earth, which means when it sends a signal back to us, it takes 23 hours for the signal to get to Earth. We don't talk to them very often, but they check in with us once in a while. Voyager 2 is 12.8 billion miles from the Earth. It's going a little slower. It's about 19 light hours away. These spacecraft are older. They're challenged. Sometimes things start to not function. The team that's still working on these, there is a full NASA team that works on these. They do a lot of problem solving. One of the thrusters will go out, and they have to figure out how to work around a thruster that's not doing what they want it to do anymore. But so far, they've done amazing jobs figuring out what they can keep functioning. Most of the equipment is still working, at least at some level. So these have actually left the solar system. During the time they were in the solar system, they collected solar data, including solar wind data, all the way out. There are best readings to the edge of the solar system. And then one day they passed through a point where the solar wind data stopped. And they stopped picking up solar wind data because they're on the other side of the magnetic field of the sun. They're outside our solar system. They are literally in true interstellar space. So they're still picking up particle data, but it's not particle data from the sun, it's particle data for particles traveling between the stars. But they were the first to collect that data. Okay, so, like I said, I didn't want to go through every solar craft out there. We could be here all day. But those are some of the oldest, the newest, and the up and coming. Questions? Okay. Just 1 second here. I'm going to bring you a mic. I don't need this. Just because we are streaming. All right.
Okay, I had a question about Parker.
Yeah.
Because you said it is going inside the corona, right?
That's true.
And the corona can get to like a million degrees.
Yes, it can.
Parker can only survive 2,500.
Yes.
So how is it surviving inside the corona?
Super good question. So it has to do with the temperature as well as the density of the gas. So if you think about your oven, if you reach in your oven and you grab the rack, you're going to burn your hand. But if you just stick your hand in the oven and don't touch anything, you won't get burned if you don't leave it there too long. And the difference is the density. So the metal is very dense. When you grab it, you transfer a lot of heat very quickly. The gas is less dense, so there's fewer particles touching your hand. They transfer heat to you slower. So that's the key for Parker. Because it's going through the atmosphere, even though it's hot, it's very, very thin. And so as long as it doesn't stay in there too long, it'll be okay. So it's like, as long as you stick your hand in the oven, pull the cake out, you're okay. But don't forget to put the hot mitt on before you grab the cake. So, no, that's a good point. Like, they wouldn't want to go in and hang out. Yeah. Other questions? Okay, we'll pass it down. Thank you. That'd be awesome.
Again, this is about Parker. You
Fire.
mentioned if the mission extends, it'll keep orbiting and getting closer and closer. So is one likely scenario it'll just go closer and closer till it burns up, or is there any way it can back off?
I think the goal is to not get it that close, because they can control those orbits. So we'll see. It will depend on how long NASA keeps extending it and how daring the mission team decides to be. And I think some of that will depend on this first pass, right? How does it go? And then they can decide just how much closer they want to creep each time they go in. It is a good way to end a spacecraft, right? At the end of its life, they did that to the Galileo space probe that was orbiting Jupiter. At the end, they just plunged it into Jupiter. So, who knows?
I was just wondering, they launched the Voyager 1 and 2 in '77. How many different directors have they had for the program?
Oh, that's a good question that I do not have an answer to. I apologize, but no, a lot, because they'll typically work a few years and then they'll move on to another project. But yeah, I don't know. But I know they still have an active team on it because Voyager 1 just had a thruster problem. And they thought they'd lost it, and took them a month or so, but they figured it out, and it's good to go again. So mostly that's when we hear about it, right? When it's having issues, then they do press releases. But
So this is about the Voyagers as well. So you're saying about the thrusters. How do the thrusters work if they've been out there for so long? They probably don't have any more fuel.
yes, so they do, but not a lot. The bigger challenge with the thrusters is that the pipes are starting to get clogged. And so the fuel lines are getting smaller and smaller and smaller. So you're still trying to push little bits of exhaust and fuel through these tinier and tinier and tinier pipes, which makes them less and less efficient. And yeah, it's a problem. But it's not like you can send somebody out there and be like, just put a thing down there and clean it out, right? It is what it is. So at one point, they'll cycle through them. They do have 3 axes worth of stabilization. So sometimes we'll turn off those and we'll use these ones. And then at this point, they've come back to one they used to they decided not to use, but now they're the better of the ones that they have left. So they just keep, that team is super creative. What can we do with what we have?
So for Parker Solar Probe in particular, I imagine that most of our solar observing satellites are powered typically through solar panels or anything like that. For Parker, because it's so close to the sun, is there any other way that it's powered that will protect any solar panels, or does it use a different system to power it?
So typically when they're not on solar, they're on nuclear. So you can, normally when it's close to the sun, you don't need the nuclear power source because you've got the solar panels. But if you're going to shut the solar panels down, the nuclear is your backup option. And nuclear power works great. That's what's running Voyager, right? Voyager's way too far away from the sun and has been for a long time. Pretty much anything past Mars rarely has solar panels. So they run a nuclear reactor. It's not very big. It's not like running a nuclear sub. You need a small amount of nuclear material that generates a potential that generates electricity. Yeah. The other challenge with spacecraft is you don't have a lot of electricity, so you have to keep whatever you're using very power low, right? If it's going to be a power hog, it doesn't get to go on the ride.
I have a quick question.
Yeah.
So with the Voyager probes, there was that whole termination shock.
Yes.
Is that the point where the solar wind just stopped?
Yeah, it's sort of where the interstellar space pressure reaches the sun's pressure, and the two balance each other out. And so you're not quite out till you get through the helio sheath, but you're right on the edge. So you've sort of reached the edge of the pressure and then the edge of the particles.
So what's the difference between the termination shock?
Yeah,
and the
because
helio
they're not like hard edges. And so you've got particles, you have the magnetic field. We definitely at this point know we're beyond both. Any other questions?
I think I have one.
Okay, I will try to have an answer.
I should know this, but I don't. At one point, there was or there is going to be a satellite that's going to actually, they're going to crash it into the sun. Is that one of the ones that was listed? Crash in, they're going to have it fly in?
I think so, but off the top of my head, I don't know which one that is. So there's always, too, the spacecraft come in multiple kinds. They're the ones I've proposed that nobody's actually picked up yet. There's the ones I've funded, or that I've proposed and NASA's funded. There's the ones I've, not me personally, right, but the team has proposed and we are building. So I don't know if that's one that's been picked up yet or just talked about. Europa Clipper, for those of you that are watching Spacecraft, right, we're about to launch a spacecraft to Europa. This is a big deal. We've been talking about this for like 3 decades. And they finally, after many, many submissions, got one funded, and it launches this year. It's going to be huge because it will be our first spacecraft in orbit around Europa. But I've watched that one sit there and spin its wheels for a long time while we waited for it to reach sort of the highest priority.
So this one's actually about Europa itself. This is just me confirming something that I think I know. Isn't that one of the moons that has a potential for life that we think?
Exactly. So Europa is the one with the ice shell around it with an ocean under it. And until we get a spacecraft in orbit around it, we do not know what that ocean looks like. That's why we care so much. Because it could be ice with a liquid ocean under it, or it could be ice with a slushy underneath it. We know it's fluid, but is it mostly ice with a little bit of liquid, or is it mostly liquid with a little bit of ice? Until you can see the tidal bulges created by Jupiter on it, you don't know. So we will have all sorts of information very soon.
And
So
that's
very
the one that
exciting.
has the ice that spews out of it as well, right?
Yeah.
Okay, cool.
Yeah. And when it cracks the ice, water, liquid of some kind comes out from underneath. And where you have water, you have the chance of life. So it gets very exciting. So yeah, watch for Europa Clipper. That's going to be a big deal very soon.
October the 10th.
October 10th.
Do you know what the launch craft is going to be?
I don't. Sorry. It's a good question. I'm not sure.
I mean, that's the ways out there, is it?
It is. And I don't know if what they're using for, but it's close enough to launch. You should be able to Google that one. It'll tell you what they're
Okay.
setting it up on. Sorry. All right. I would like to end with just a quick couple reminders of upcoming events. So October 19th is our star party. We have an in-person community star party out at the SIU Dark Observing Site on the farms. We'll have a bunch of telescopes out. We're going to have activities and games and all sorts of things. It's a big family-friendly event. People can come and go. We'll be looking at the sun starting at 4 o'clock. Make sure you have a filter before you look at the sun. But we'll be doing that, and then as the sun goes down, we'll switch to star viewing. We will also be live streaming that event. So the SolarSTEAM website will have a live running show, like we did for the eclipse, about the event. And then the Journey to the Sun talks, this was talk number 1. We'll be running 2 more this semester. The next one is Dr. Justin Schoof from the School of Earth Systems and Sustainability. Did I get that right? Yes, okay. And he's going to be talking about the Earth's climate and how the sun affects that, because there are times where you would think it would cause it to go one way, but it doesn't. It makes it go the other way. So we'll look at some of those odd puzzles of why it's doing what it's doing. And then on December 6th, Peggy Hill will be talking. Dr. Peggy Hill is a retired faculty member from SEMO. She is also a NASA Solar Systems ambassador, and she'll be talking about this space weather we were mentioning and how it impacts us, right? Why do we care? And then in the spring, we'll have 4 more talks. Those will also all live stream on the SolarSTEAM website. So join us again. Thank you for coming. We appreciate you turning out, even though it's pouring rain out there. So have a great weekend.